So given a matrix A, we're going to introduce the idea of eigenvalue and eigenvector. And these are eigenvector. These are our special scalars and vectors that share a unique relationship with the matrix A. So if V is a vector, a non-zero vector, and lambda is any scalar, then we say if V satisfies this relationship. So A times the vector is the same thing as scalar multiplying that vector. Then we say that V is an eigenvector for the matrix A, and lambda is the corresponding eigenvalue for the matrix A. Let's see an example of this in action. Let's say we have the matrix A is 4, 3, 1, 2. Let's just verify that lambda equals 5 is an eigenvalue, and the vector 3, 1 is an eigenvector for that eigenvalue. Let's go and check this. So let's first take A times V. We want to verify that this is actually lambda V. Lambda V. So A times V is 4, 3, 1, 2 times the vector V, 3, 1. We want to check, is this the same thing as 5 times 3, 1? Okay, so to actually perform this operation, we'll dot the first row with the only column. That's 4 times 3 is 12, plus 3 is 15. And then for the second entry, we dot the second row with the only column, and we get 3 plus 2 is 5. And then for the right-hand side, we multiply this through, and we get 15, 5. So that actually checks. And this matrix multiplication actually takes a fair bit of work, whereas scalar multiplying is faster. So there's definitely, if you can identify the eigenvalues and eigenvectors for a matrix, it can speed up considerably a lot of the computations. So that's how you would check an eigenvalue eigenvector. How about finding them? So finding eigenvalues and vectors. Well, the idea here is you're looking for a vector V that satisfies this equation. And just want to point out here that if V satisfies this equation, we can multiply both sides of this by C, by any scalar C, and do a little bit of associating. And we see that if it holds for the vector V, then the equation also holds for any scalar multiple of V. And since V was not the zero vector, then we see that we have a lot of solutions. There's actually an infinite number of eigenvectors that satisfy this equation for a given eigenvalue. So we want there to be many solutions. Non-unique solution. Okay, so if we take this equation and manipulate it a little bit, this says that AV minus lambda V equals 0. Now, the 0 on the right-hand side, is it a scalar or a vector or a matrix? Well, A times V, if you multiply a matrix times a vector, you get a vector. If you multiply a scalar times a vector, you get a vector. Vector minus vector gives you the 0 vector. Not the 0 matrix, not the number 0, the 0 vector. Okay, now on the right-hand side, or left-hand side, I'd like to factor out a vector V. But if I do that, if I factor a V out of both of these, I have A minus lambda, a matrix minus a scalar. That doesn't make any sense. We can't actually combine those together. So we do this little algebraic trick of writing this as lambda times IV. Because if I take the identity times any vector, it hasn't changed. Then we'll just reassociate those together and write this as AV minus lambda IV is the 0 vector. Now if we combine these together, this gives us A minus lambda I times V is 0. And remember, we're looking for non-unique solutions. It means we do not want this to have a unique solution. That means we need the determinant of that A minus lambda I to be 0. Because remember, if it's non-zero, there's a unique solution. If it's 0, that means there's not a unique solution, and that's the case we're looking for. We want there to be multiple solutions, so we're going to solve that equation right there. And then once you find your lambdas, then we'll go back and plug them into this equation right here, and be able to solve for the v's. Let's do an example of this. Let's maybe look at a 2x2 case for now. Let's in fact go through and solve the matrix that we just had a minute ago. That's this 4, 3, 1, 2. So let's take A to be 4, 3, 1, 2. And let's go through and find the eigenvalues and eigenvectors for this. So remember, we need the determinant of A minus lambda I to be 0. And that's the determinant of, now the matrix A is 4, 3, 1, 2, minus lambda times the identity. If we take the identity matrix and multiply it by lambda, we've got this. We want this determinant to be 0. And now we'll combine those matrices together. So this is the determinant of 4 minus lambda, 3, 1, and then 2 minus lambda. And we want this to be 0. Let's go through and take the determinant. So we do that cross multiply business. We've got 4 minus lambda, 2 minus lambda, minus 3 times 1 equals 0. Okay, if we FOIL this out now, we've got lambda squared minus 6 lambda plus 8 minus 3 equals 0. And then this we can combine these together, lambda squared minus 6 lambda plus 5. And this will factor up as lambda minus 5, lambda minus 1. So that says we've got two eigenvalues here. Lambda equals 5, lambda equals 1. Okay, now, so that says we've got two different lambdas. Let's go and figure out what the eigenvectors are for each of those. So what we'll do is start a new sheet here. Remember, we want to solve A minus lambda I V equals 0. So in our original matrix, A was 4, 3, 1, 2. And we found lambda to be 5 and lambda to be 1. So we're going to have two separate scenarios here. So first, let's look at what happens when lambda is 5. And then we'll look at what happens when lambda is 1. If lambda is 5, we're going to take A minus lambda I. So that gives us, now if we subtract 5 along the diagonal, that leaves us with negative 1, 3, 1, negative 3. And remember, we're setting this equal to the 0 vector, so we're going to augment this with 0. So now we can row reduce this. We can add the top row to the bottom row. We've got negative 1, 3, 0, and 0, 0, 0. Now anytime you're finding an eigenvector, one of your rows should always 0 out. And that's good that it happened in this case. So now if we multiply the top row by negative 1, this gives us 1, 3, 0, 0, 0, 0. So I see that the y-coordinate is free. That should be a negative. So the y-coordinate is free, and so the x, this is x minus 3t equals 0, so x equals 3t. And that says that our eigenvector is 3t comma t. Now t is arbitrary, so we can actually factor it out. So this gives us t times the vector 3, 1. So this right here, this 3, 1, that's the eigenvector we're looking for. In fact, any scalar multiple works, but this gives us a good eigenvector to work with, 3, 1. So that actually verifies what we did on the previous problem. So for the eigenvalue 5, the eigenvector is 3, 1, or an eigenvector is 3, 1. And then for lambda equals 1, let's do the same thing. We're going to take A minus lambda I, that means subtract 1 along the diagonals. That gives us 3, 3. And we subtract 1 from here, we get 1, 1. And again, we're setting this equal to 0, so we're going to augment this with the 0 vector. And now we can take negative 1/3 of the first row, add it to the second row, and that leaves us with 3, 3, 0, 0, 0, 0. And then divide the top row by 3. We've got 1, 1, 0, 0, 0, 0. And so this says that y is free, and x is equal to negative t. So that means our eigenvector for this is negative tt, we can now factor the t out, and we've got negative 1, 1 for an eigenvector. So that's how you go and find eigenvectors and eigenvalues for a matrix.